All right, we're going to start gas law stoichiometry. So this is just to remind you. So at STP, we're going to use this PV, it was NRT, right? So STP, 1 atmosphere, right? We don't know what the volume is, so we'll figure that out. We're going to use 0.0821, right? Atmosphere times liter over moles times Kelvin. And then 0 degrees Celsius is 273. So if we solve this, the volume you should get is about 22.4 liters. So that means in 1 mole at STP, there's 22.4 liters. Hopefully that ratio is familiar to you. And this only applies at STP. So we can use this in stoichiometry problems. So let's look at the next one. So given the following reaction, NH4 NO2, ammonium nitrate or nitrite equals produces nitrogen gas and water, which is gas. How many liters of nitrogen gas is produced if 50.0 liters of water is produced at STP? So here, the water, we need to add a 2 there. You got to balance your equation before you do stoichiometry, right? So if you think about it, we're starting 50 liters of water, so there's 50 liters of water, and we want to know how many liters of nitrogen, right? So if you remember, this is a molar ratio. Oh, sorry, this is a molar ratio here. So we have to convert these into moles. So if I have 50.0 liters, now this is at STP, and we want to convert to moles. We just did we know that we just did the ratio, right, or the conversion factor, 24 liters of water in 1 mole of water. And then we know from here, for every 2 moles of water, there's 1 mole of nitrogen. And then we know how many liters of nitrogen gas. Well, we know in 1 mole of nitrogen gas, this is a gas at STP, right? We have 22.4 liters of nitrogen, all right? So now what I want you to show you here is what you get is you should just get 25.0 liters of nitrogen. There's a little shortcut here, and you don't have to use this, but at STP, since if we were going from liter to liter, take a look here and here. Do you notice you multiply by 22.4, but you also divide by 22.4? And so the shortcut is this. At STP, this only works at STP. This ratio of like 1, 1, 2 is also a volume ratio, meaning it's also a ratio of liters. What I mean by that is we could have just gone straight like, okay, 50.0 liters of water. We know for every 1 liter of nitrogen, there's 2 liters of water. So for every 2 liters of water, there's 1 liter of nitrogen. And so you get 25.0 liters of nitrogen. This only works if you're going from a volume to volume. So, and it only works at STP, okay? Oops. Okay, so this reaction. So as soon as I see STP, I'm thinking, okay, I can actually do a liter to liter. But do I need to get to liters? The answer is no, right? I'm trying to actually get to the mass of copper. So in this case, I can't use a liter to liter ratio because I'm not going to liters. I'm going to copper. So in this case, I start with 250. First of all, we got to make sure this is balanced, right? So it looks like it's balanced. So the ratio is 1. So I'm starting with 250.0 liters, 250 liters of hydrogen gas. I'm gonna have to use 22.4 liters of hydrogen. This will give me 1 mole of hydrogen. Right? And then once I get into moles, I'm here, right? So for every 1 mole of hydrogen, I get 1 mole of copper. And then for every 1 mole of copper, I just use the molar mass, right? So copper is 63.55 grams of copper. So 250 divided by 22.4 times 63.55. So then my answer is 709 grams of copper. Okay. All right. What about the case where no STP, right? So let's take a look at this first. Ammonia can be synthesized from nitrogen gas plus hydrogen gas, while volume of ammonia at 450 kilopascals and 80 degrees Celsius can be obtained from the complete reaction of 7.5 kilograms of hydrogen. Okay, so we probably need to balance this first. So this would be 2 and this would be 3, right? Okay, so you're starting with 7.5 kilograms of hydrogen, right? And we want to figure out the volume. We want to know the volume of this. So ultimately, we're going to use PivNert. Okay, so ultimately, we're going to use PivNert to figure this out because we got to figure out volume. But PivNert requires, what do we have? We have pressure, cool. We have temperature, great. We want to figure out volume, so we need the number of moles. So we need the number of moles of ammonia. So I'm starting with 7.5 kilograms of hydrogen gas, and actually I'm going to go ahead and figure out the number of moles of ammonia. Okay, so for every 1 kilogram, there's 1,000 grams. And then also, we know that, now we're going to convert to moles, right? So 2.02 grams of H2 equals 1 mole of H2. And for every, now I'm going to use the molar ratio, 3 moles of H2, there's 2 moles of NH3. So at this point, times 1,000 divided by 2.02 times 2 divided by 3, 2475, I'll just go to that number, sig figs, moles. Okay, so I have that many moles of NH3. So now I can use that and plug into this equation. So PV equals nRT, right? So we have 450 kilopascal. Our volume is what we want to solve for. We now figured out the number of moles. We're going to use 8.31 because we got kilopascals, right? And then we're going to use, what is it, 80? So 80 plus 273 gives me 353 Kelvin, right? So we're going to solve for that. Oops. 2475 divided by 450. Yikes. So our volume is going to be really big. Let's say 1.6, 1, 2, 3, 4 times 10 to the 4th liters. Okay. So just to remind you, a lot of these problems, you have to use PV equals nRT when it's not at STP. You have to use the ideal gas law, and oftentimes you'll have to use stoichiometry to get the correct number of moles in the correct in whatever reactant or product you need. If 34.6 grams of zinc are reacted with an excess of hydrochloric acid at standard pressure, what is the temperature of the hydrogen gas produced if it occupies a 20.0 cubic centimeter container? All right, so okay, so first let's balance this equation, right? So you got 34.6 grams of zinc. So we have 34.6 grams of zinc. But our PV equals nRT. We want to figure out hydrogen gas. You guys see that? So hydrogen gas. We want to figure out, this is where we're going to use our PV equals nRT. So we have we need to know the temperature. We have pressure. We have volume, right? We just need to figure out. So first we're gonna convert our grams of zinc to moles of hydrogen. And we need to balance this guy, right? So I think there's 2. That'll be just fine there. Okay, so let's do our stoich. So we got 34.6 grams of zinc. Let's convert that to moles, right? So zinc. 65.38 grams of zinc for every 1 mole of zinc. So for every 1 mole of zinc, you get 1 mole of hydrogen gas, right? That's our ratio, and that's it. So 34.6 divided by 65.38, 0.529. I'm just going to keep an extra. Okay, so that's our moles of hydrogen gas. So now what do we got to do? So we know this pressure, it's 1 atmosphere, right? So it's a standard pressure. So PV equals nRT, 1 atmosphere. We got 20.0 cubic centimeters. So 20.0 cubic centimeters equals 20 milliliters, right? And remember, there's 1,000 milliliters in 1 liter. So this would be, if you did the math, it would just be 0.02. There's 3 stick figs here, by the way, liters. We just figured out the N. That's N right there. So 0.5292. R is 0.0821 times T. All right, so let's see if we can figure this out. Ooh, temperatures. So our temperature would be very low, 0.46. One more. Kelvin. Okay. And that would be, I mean, you could subtract 273. It'd be very close to absolute 0, right? Okay. Hopefully that helps.